Thank you, everybody, for being here in our subconscious. Yeah, for our second talk of this season. Today we're gonna hear Dr. Jorge Matrínez Ortega. Dr. Jorge Matrínez Ortega is also an old friend of mine. He was with me when we were doing our bachelor in physics. And then he studied his master's and his PhD in particle physics at Staff in Mexico City. Then he went, in that time he had several periods of, he spent quite a lot of time in Fermilab and also in Chile. Argentina, sorry. And then he did a postdoc in the Bell2 project in Japan, also in particle physics. Then he came back here to Mexico and worked at the federal government as a data scientist and also in a company called greSQL, which is also related to data analysis. And then he is now currently working at the state government, also as a data scientist. He is going to talk us about the managing and processing data implementation in public data administration, and this the typical work they are doing there, and that this here are going to tell us about the techniques they use and what are the current problems that the administration faces and how they solve this kind of stuff. So, Dr. Martinez, pleasure to.
Thank you for your presentation. So only to be a bit more specific, during my PhD studies, I was working in the D0 collaboration, and I earned the privilege to be a collaborator. So that was the work during my PhD studies, and during my postdoc, it was in the Bell2 experiment, as Pablo mentioned, in Japan. So I was also in Argentina, but in the Pierogen experiment, but I was not part of the collaboration. It was only estancia. I don't know how to translate it. Okay, so I will mix a lot Spanish and English because but I try to prepare my talk in English, but probably I don't remember all the things I want to say in English, so let's try. So this is the outline of the talk. I will give a brief introduction about data processing. Then I will describe two main ideas about data pipelines. I will talk about something about open source, like different flavors of open source. Also, I will describe some of the tools that we are using every day in the data analysis process. I will talk about an example in real life and two possible solutions of this example. Then I write down something that could be conclusions or some random thoughts. And I will put at the end some extract from D0 publication that is very concise about what does it mean this collaborative open source. It's an example of how to do it. And I will talk about the details when we reach that point. So, as an introduction, this is only my view, and probably could be a lot of controversy here, but to me, it's essential in physics, the experiment, because nature requires that you test that your theories behave as you think. And of course, data is essential for the experiments because once you perform an experiment, you want to store the data and keep it to do further analysis as many times as you need because we are humans and always make mistakes. Of course, so it's important because it helps us to create simulated data. Of course, there are another useful things, but I'm focusing now this topic as an experimentalist. So with these three points, these three starting points, then we have some questions. So how do we should deal with this data? Then do we perform something that can be versioning my data? And after that, I process my data with some software or some tools. Do I version these different pieces of software? And then how do I assure reproducibility of my data processing analysis? This is crucial for building knowledge because you can claim to do something, but if nobody can reproduce it, so it's like if it's not there. Some weeks ago, I learned about this hypothesis about some disease in the brain that is related to some protein that accumulates in the brain. And I don't remember the details, so I'm just talking like an anecdotic example. And then this publication, like 10 or 12 years ago, appeared a publication saying that this protein was the main cause of this disease. I think it's Alzheimer. And I think protein is something like beta amylase something. But it seems that nobody can find this protein except the original authors. So this is something that can happen in every day in science. So we don't want that as physicists. So this is just an example. So my background is as a experimentalist particle physicist. So I will start with that and explain a little bit what does mean data analysis. So the detector, here is a small drawing. I didn't want to put all the details, but I will do some draw here to talk about this. Or maybe if some of you know the structure of some general purpose detector, can you remember? No? Nobody? No? Okay. There. Okay, the main idea is for general purpose physics, high energy experiments. We have some path where our particles travel. It can be a line or it can be a circle. And then at some points, we make those particles traveling inside this path collide. So this is a linear experiment. This is a circular experiment. And then what do we put here? So we have to put several layers of detectors. So let's take a cross section here, one experiment, and then what do we have? First, we have a pipe where the particles are traveling. One in this side and the other one on the other direction. So after this pipe, So here is not a scale, of course. We have some detectors around this. Why do we have this? Because when the particles collide at this point, they go around several trajectories. So you have to put some material here to try to guess what are the trajectories. So nowadays, this material is usually silicon detectors and could be several types. They could be strip, like cords of silicon, or they can be pixels, like small squares, uh, uh, placed in some big plates. So, for example, the CMS experiment has 70 million silicon channels. So they have a volume 70 million, a lot of electronics to read out electric signals that are uh, being generated at the moment the particles travel through the detectors. Then we have some wire or fiber detector. They can be scintillating fibers, or they could be a chamber with metal wires and some material that when some charged particle travel through this whole area, uh, some free charges are generated, or in the case of the wires, or if they are fibers, then they produce some light. So after that, we have other detectors that are also scintillators, but these are not to try to reconstruct trajectories. It's instead to create some flag on these events that they contain electrons or photons. Then after that, we have bigger pieces of equipment. They are called calorimeters, and they destroy the particles that, not all the particles, but some of the particles that arrive to this detector and tell us how much energy they have. Uh, then usually, I would say all the experiments, but probably there is some that one that does not have a big magnet around. Uh, well, if we didn't have a magnet or a magnetic field inside this detector, the trajectories wouldn't be pure. They would be uh, straight lines. But with a magnetic field, the charged particles can deflect from a straight line trajectory. Then we have some other scintillators here, usually with less resolution, bigger pieces. Scintillators here and here to detect muons that can travel across the calorimeters and across the magnet. Also, some protons and ions can travel. So this is more or less the general composition of a detector. So first, silicium, then fibers, then scintillators, then calorimeter, and then neurons. So all this equipment has its own electronics to the readout process. So we, as physicists, we have to interpret these electric signals to something that makes sense to us, like momentum or something like that, velocities, rapidity, etc., mass. So each of these has its own ad hoc electronics, and not all of them function at the same rate. So you have to adapt to the slower rate, of course. But why do we do this? Because there are a lot of events generated in this process. So these detectors and these detectors usually are the fastest detectors because they only measure some light, and they serve as triggers. So when we have some event that reach this detector, we know that there is a neon in this event. And sometimes it could be interesting to study events that have neons. So this is only this part of the diagram.
What do you mean by the faster detector? Is response time is small.
What?
What do you mean by fast detector? Means response time is small.
Yes. Yeah, I think in the D0 experiment, the fastest electronics we had, it was like 2 megahertz or something like that. Yeah, but we had to reduce that because not. So this means that we have 2 million events per second, but not all of these events are physics events. Only a readout signal. Then you read that, but you don't want to store everything. At the end, the D0 collaboration only stored at 50 hertz. So we have to reduce from 2 million of events to 50 events per second. So, okay, so then this is only this part. After some triggers, we decide to save some events, but this data is not ready for physics. So we have to do a lot of reprocessing that is shown here. And we have to separate in different events, and not all the events are necessary for all the physics analysis. So we have to also do some codes to the specific physics that you are looking for. So during all this process, we have to take some data, do some process, and generate new data. And that's like the story of everything about data processing. No? Starting point, process, final data. But final data could be the raw data for something new. So how can we divide this process, this data process? There are two main paradigms, I think. So one is batch data processing. Given k events, and we have to perform n processes over them. So batch data processing, we start process 1 for the whole batch of K events. Then start and complete process 2 for the whole batch of K events. But there is another point of view or another way to do it, that it's called continuous data processing. It's also discrete, but the batch is here is one event. So it's take one event and perform the n processes for this event. Then take event 2 and perform the n processes for this event 2. And this can be done in parallel. This can't. That's the difference. Some questions here? Everything is clear? Okay, so these are the two main paradigms to deal with data, but not only that. So we have to create some pieces of software that manipulate our data, and we frequently want to share these pieces of software with other collaborators or with the world. So it's common that in experiments we use some open source license to share these algorithms. And there are several kind of licenses. Some that it's useful to mention is the GNU General Public License. That is the license under what Linux is distributed. This means that all the software that you publish can be used in any way that anyone wants. But if someone takes your code, they have to publish a code also with the GNU public license. That's very restrictive because once you use open source with this license, and all the people that use your code also has to open your data. We prefer something less open, let's say. For example, the MIT license that allows to close your software in any moment you want. So you can use it, anybody can use it, if you can find it, but you are not, it is not mandatory that if you use some piece of my software, you have to open it. You can keep it closed. So it's more popular. It's less restrictive. And also, I don't know what is this, but there is also the Apache public license, and probably BSD license is also very common in some software, and I didn't know that there was a Python license. So, this is public in the open source initiative web page. So I wanted to show you in order to know that you don't have to reinvent the circle. It's there. So then we need to process data. We like open source, and what can help us with this task? So there are several tools that can help us with this. I would say that the main one is Git. That is a version control tool. This tool help us to avoid this very common practice that we have when we are creating some intellectual work, like our thesis or whatever, because it helps us to avoid the practice that thesis dot final, thesis dot final final, thesis dot final final for real. So with this tool, we have an order process to do that. Also, help us to show to other people or collaborators our code or our job to reach a consensus or to find mistakes. And then it helps us to classify the stage in which the code gels. Because if it's only a prototype, then it's in the feature branch. Then if it's accepted for others that can be helpful, then it's in the develop branch. If it's ready in some environment that replicates the real scenario, then it's in testing branch. And it's in the real scenario, then it's in production. And other useful tool is Docker, because instead of creating one application that solves all the problems that we have, we can divide all the problems and focus on one. Then solving the first problem with one microservice that take our data, and the output is something that is more useful to us. And then we can connect this output data with other microservice, but probably it's not ready. So in the development process, we can separate it. We can find or perform an abstract solution for each of the problems, and then connect them as they become ready to use. And also, they allow us to create recipes. Sometimes we have a set of tools that have to install in our working environment, and that requires like 8 hours or something like that. With this tool, we can create something like a script that we can execute with one click, and then all the steps are performed to create a virtual machine that has all the software that we need. So that helps us a lot. Then Python is a general purpose language and can be used to do some object-oriented programming or functional programming, and also for scripting like Bash. Then we need some database. This is like a commercial PostgreSQL, SQL, that is the one that I like. There are several flavors for SQL, also open source, but they claim this is the most advanced DB in the world. They themselves claim that. So I believe them. And some frameworks, HTTP. I wanted to talk about this because this protocol was invented by a physicist, and is the protocol on which probably most of the internet relies on. And Tim Berners-Lee, physicist, was working at CERN, and he developed in the 90s, 1991, this protocol. And it's the protocol that the browser uses to get the HTMLs that are in other computers. So in Python, there are three popular frameworks. Flask is the simplest. Django is like everything is on there. Like if you want to kill a fly with I don't know. With a canon, this is a canon. And fast API is the most popular now, and it's also as simple as Flask, I would say. Also a little bit more complicated frameworks, but they are also useful, and I will show you a problem that is using an implementation of this framework called Redis. And these technologies allow you to store and implement, store events and implement a design pattern called publisher subscriber. So just a little bit of this. So this pattern allows you to solve the problem that we have this channel of events. One, that some events are here happening, just happening, but who knows that this is happening? So you have to create a subscriber that can read these events. For example, this is event one, A1, this is B1, this is A2. So we can have several kinds of events happening here. So like these classes are the same. These classes are the same. And then this also the same. So for example, this is subscribed to A. So then we only focus on these channels. And then we can create some other rule for another subscription like B. And then this knows about only the B events. So problems that can be described in this way can be easily solved with this framework. Okay. So here is a real life situation that we're encountering in big data. So we have here a citizen going to institution 1, and we have other citizen going to institution 2, and these two institutions are required to send the data to a third institution. So let's say that we want to know the identity of the citizen. So we have this function that is like atención ciudadana of this institution 1, and they receive the name, the last name, both last names, the birth date, some alias, I don't know, like the place of birth, and the date of one event. So the citizen goes to the institution 1. This then send the information, creating an ID that is a function of a subset of the variables here. It's a unique ID. Could be some encryption of this data. This helps us because we can reproduce the same ID with the same information. And if there is no previous existence of this ID1, then we can push the event there. Institution saves it and tells us that everything is okay. Then the second citizen goes to second institution. The second institution creates an ID that is a function of a subset of the variables, but they find that the ID1 and ID2 are the same, because it could be that the n primes are, well, the prime variables are equal to the variables with no prime. And then this institution does not accept this second event. So what can be a possible solution to this? Well, the first solution is kind of simple, because we can add a random event in our a random variable in our subset of variables, and then we can again encrypt our information, and with these two random variables, they shouldn't be equal. So then it allows to push this event to the fifth institution. But what if the information really was the same? So what if we are focused on answering the question, are these two people the same people? So this solution only solves the way we store the data, but we don't know if the information is redundant or not. So this is the implementation in real life in some federal institutions, and it's causing some problems because we don't know if some events are repeated or not. So we have to change a little bit this paradigm. So a possible solution that we are working on right now is take this more complex situation. Again, we have the citizen going to institution 1, and then we create an ID with a subset of the information that the citizen gave us, and everything is okay until here. Then another citizen gives some of the information, and presumably they form the same ID, and this institution tells this institution, the third institution tells to the second institution that these two IDs are the same. So then this institution has to do something with that information. In the previous scenario, we didn't have any feedback from the third institution, only that everything is okay. But what happens when it's not okay? So then we create this intermediary step. We inform the citizen that we found some register in the other table, and then we have to find a consensus on the information. The citizen has to tell us, is this real? Is this information what you are trying to telling me or not? If it is the same information and the citizen confirms, then we can resend the information with probably some modifications with the ID, taking information from the two IDs that we had before, this one and this one. And then we have to insert this new ID in this database and link it. We have to establish a relationship between this and this one. So that it's easy to tell, but it requires a lot of effort to implement, and we are working on that. So this simple drawing or abstraction of implementation, it already requires something like that, like this, and all the technologies that I mentioned before. So here, of course, there are other situations when there is no match, and also there could be the situation that information is not exactly the same, but for example, if there are in the specific situation that these two citizens are looking for someone, and they tell the information of the third person, and there are small discrepancies in this information, how do we know that they are talking about the same person? So we have to also try to find some possible matches, possible coincidences on this information, but it's more complicated than this. This is the case where some exact match exists. Some questions?
Since you said that it's a real life situation, can you say something about the amount of, say, how many of these events do you have, and what is the percentage, or how likely is it that you will encounter? Do you keep track, let's say, about statistics, right?
More or less.
Or how frequent these problems are?
More or less. So let's say that in this database there are around 15,000 events, and here like 3,000 events, and around 80% of the data here. So let's try to write. Institution 1 has around 3K events. Institution 2, it has around 15,000 events. So here, there is a subset around 2,000 that are the same event, like exact matches with the same information, and some 700 events, more or less, that they have like a fuzzy match. So it's not that you can find the exact information in two entries, but several pieces of information have some coincidence. And what else? Institution 3 has even more events, 20,000, that are, I don't know, like 15,000 come from E2, almost the 3,000 come from Taiwan, and the rest come from even other institutions. So finding a consensus between these two is not that hard, but finding a consensus with this one is even harder. We have more events and even more institutions here. Also, I am not talking explicitly about the dates, but there could be some coincidence in names, but the dates can be different. So and they can be different by several motives, because they are really different events, because there is some incorrect information, or like the dates are displaced by 1 week or 1 day or something like that. But they are actually the same event. So we have some, I would say, the quality of the data is not perfect. We have several mistakes in the data taking and also sending the data. So we are focusing on that. Well, I have no other details about this problem, but it's the kind of problems that we are finding to is every day in public data. Some other question? No? No? Because I'm ready to say my conclusions. So my conclusions is not real conclusions, but are like random thoughts. So data is there, and there are plenty of sources of data, and also open source software for data processing is there, and they are really useful tools. So if we take the time to learn about these tools, they can help us with the duty of analyze data. And I would say that as a scientist, we have the duty of take care of valuable data. So if we do not try to understand the data, then who else? Who are the scientists? I think that we have to do something valuable with this data. And also, I want to emphasize this. So there are many tools that can help us to lighten this burden of data processing, systematizing and helping us to share with others. And software is collaborative, and of course, knowledge is collaborative. I want to emphasize also that. And in that line, I wanted to show this example of this extract from a manuscript. All the manuscripts in the Zero collaboration had a disclaimer saying that whatever you do, you don't take responsibility of the use of that. That's something basic in the open source. So the ultimate responsible for whatever process software does is the user. That's a mantra in the open source. So you have to be responsible to know what you are doing, taking software from other person. So first, this is a disclaimer. Then, how are you allowed to distribute that software or that manuscript, and what who has the right to take royalties or whatever if you are charging for the use or if you are not interested in that, like the copyright notification. And I wanted to show you this because this sounds like an abstract idea, but the only thing that you need is only write it down, and the user is who takes responsibility to know all of that. That's the mantra of the open source. And I think that's everything I wanted to talk today.
So we thank Dr. Jorge Martinez for his very interesting talk. Does anybody else have a question? Well,
Yes.
Yes,
Could you give more details about this amount of data? I mean, in this experiment, and how to compare with the government application that you do?
Yeah, I don't remember all of this, but I think, uh, well, in this zero, we have like terabytes of data. So that was the whole sample
Per experiment?
for the experiment, terabytes. Then for my physics analysis, in which I focused for my PhD thesis, yeah, they were like several